let's have a look at this question here. Well, we have to find out the pH of a solution of, or the aqueous solution of very, very weak acid, which is given to us as HCN here. Why is it weak? Well, you can see that the dissociation constant value is so small, 4.8 into 10 to the power minus 11, right, which is very small. Now, and we have also been given the concentration of this aqueous solution, which is 1 molar. Okay, and we have to find what? We have to find out the pH. Well, to find out the pH, the first step we would do is first find out the degree of dissociation. And only then we'll be able to find out the pH. Okay, so we have been given what? HCN, right? It dissociates partially into H plus ions and Cn minus ions, right? So initially, let's say the concentration of HCN is C. At equilibrium, what would happen? Now HCN is going to dissociate, right? So it will become C into 1 minus alpha, where alpha is the degree of dissociation. And how much of H plus ions and Cn minus ions are formed in the solution? Well, they are C alpha, right? And we do know that the value of Ka, that is what? Dissociation constant, that is equal to the product of the concentrations of the product raised to the power their stoichiometric coefficients. Since stoichiometric coefficient of both H plus ions and Cn minus ions is 1, so this will become what? C alpha into C alpha divided by the product of concentrations of the reactant raised to the power their stoichiometric coefficient. Similarly, here also we have stoichiometric coefficient of HCN as 1. So this will be C into 1 minus alpha. Okay, always remember that this dissociation constant, you always find it with the concentrations at equilibrium, right? That's what we have done here. So C and C cancels out, right? Now we know that the Ka value is so small that we can neglect alpha in front of 1, right? So since alpha is so small than 1, so we can write 1 minus alpha almost as 1. So Ka becomes what? It becomes alpha square, C alpha square upon 1. So alpha square is Ka upon C, and alpha comes out to be under root of Ka upon C. So alpha is what? Alpha is degree of dissociation. Ka is the dissociation constant and C is the concentration of the aqueous solution. Now we have been given both values of Ka and C as well. So let's find out our alpha. So alpha is under root of Ka, which is 4.8 into 10 to the power minus 11 divided by C, which is 1 molar, which is 1. So we can also write it as what? 4.8 into 10 to the power minus 11. We can write it as 48 into 10 to the power minus 12 for the ease of calculation. Now the under root of 48. Let's do it. Let's make the calculations a bit easier. Instead of 48, let's make it 49, right? So the approximate value that we'll get of alpha would be 7 into 10 to the power minus 6. Correct. But how the value of alpha is going to help us to find the value of pH? That was our aim. That's what we want to find out. So pH is what? pH is minus log of H concentration of H plus ions, right? And the concentration of H plus ions at equilibrium is C alpha, right? So pH will be equal to what? Minus log of C alpha. And we know the value of C, that is given to us as 1 molar. So this becomes minus log of alpha, which is minus log of 7 into 10 to the power minus 6. Now this is just calculation. So this becomes minus log 7 minus, let's write it as plus minus log of 10 to the power minus 6. This becomes minus log 7. So minus 6, which is on the, it's 10 to the power minus 6. So minus 6 comes in front of the log. That's a property of the log. So this becomes minus 6 into minus log of 10, which is minus log 7 plus 6, correct? Because log 10 is 1. Okay, so now we just need to know the value of log 7 and we are done. So log 7 is 0.8. So pH becomes what? It becomes minus 0.8 plus 6, which is, now this is all approximation, okay? This is not equal to, this is all approximation because we did the approximation above. Instead of 48, we made it 49, right? So this will be equal to what? This will be equal to 5.2. Let's see. This will not be. This is equal to, when we add the value of alpha, which we approximated, then the approximate sign will come. Okay. So now the pH value, we have found the approximated pH value as 5.2. Let's see which option does it match. Well, it matches our option D, which is the correct option. Let's have a look at this question. Well, in this question, we have been given a hypothetical reaction, right? So in which A reacts with B to give C, and A, B, and C are in gaseous phase. And we have been given the value for change in internal energy for the reaction as minus 3 kilocalories. And change in entropy is given as minus 10 calorie per Kelvin. And we have to find the value of delta G, that is the change in Gibbs free energy for this reaction at 300 Kelvin. This is the temperature that has been given to us, right? So this is a very pretty easy question if you know your formulas. So what is delta G? Well, delta G will be equal to delta H minus T delta S, right? And we have been given the value of change in entropy, which is delta S. We know the temperature as well. But we do not know our delta H, which is change in enthalpy for the reaction, right? So first we have to find is delta H, which is given by delta U plus delta NGRT. What is delta U? That is the change in internal energy. We have been given that for the reaction in our question. What is delta Ng? Delta Ng is the total number of moles of the product in the gaseous phase minus the total number of moles in the reactant in the gaseous phase. Okay, what is R? Well, R is our universal gas constant and T is our temperature. So everything is given to us to find our delta H, which is change in enthalpy. So delta H will be equal to what? Delta U. Delta U is given to us as minus 3 kilocalories, which is minus 3000 calories, plus delta Ng. Okay, the reaction is what? A in gaseous phase plus B in gaseous phase gives us C in gaseous phase. Okay, so for delta Ng will be equal to what? Total number of moles of product in the gaseous phase, which is what? 1, right? The coefficient is 1 here. So 1 minus total number of moles of the reactant in gaseous phase. That is what? 1 plus 1 here. That is 2. So delta Ng value comes out to be minus 1. So minus 1 into R. So what do we know? We know that the value of R in calorie is 2, right? 2 calories. So 2 into temperature given to us is 300 Kelvin. So this comes out to be minus 3000 minus 600. So delta H is minus 3600 calories. That's what we have in front of us. Okay. Now we have to find the value of delta G. That is delta H. We have just recently found out the value of delta H, which is minus 3600 minus T delta S. T is 300. And what is delta S value that is given to us? That is minus 10. So this comes out to be minus 3600 plus 3000 comes out to be minus 600 calories. So let's see which option does it match. Well, it matches our option A, which is the correct option. Let's have a look at this question. So here in this question, we have been given a compound and we have to find how many geometrical isomers exist for this compound. And we have been given 4 options to us, right? So what are geometrical isomers, right? So geometrical isomers, they are a pair of compounds that have same molecular formula and they also have same structural formula. What differs is the arrangement of the groups or the atoms that are attached to C double bond C. So let's see, if we have C double bond C, then there could be what? There could be 4 groups, 4 atoms attached to these 2 carbon atoms. Now, one thing is that we have to ensure is that the groups attached, right? The 2 groups attached to the carbon atoms involved in this C double bond C, they should not be identical, right? They should be different, like X and Y. However, what would happen if they are identical? Well, if they are identical, then it will not exhibit geometrical isomerism, right? So that's why both of these groups, they have to be what? They have to be different. Okay, so what do we have here? So the conditions for a compound to exhibit geometrical isomerism, the first thing would be that it should have a double bond, right? So that's very, very obvious. And the next is that the 2 groups that are attached to the carbon involved in C double bond C, they should not be identical, right? Okay, now let's have a look at the compound that is given to us. That is CH3, CH, double bond CH, CH, double bond CH, C2H5. Okay, let's draw it. CH3, CH, double bond CH, CH, double bond CH, and C2H5. Right. So first, let's focus on the first double bond that we have here. So C double bond C, right? It has H group or the H atom. It has CH3 group, right? Another is what? H, and it has CH double bond CH, C2H5. Right now we are just focusing on the first double bond. Now, if you look at this double bond, the 2 groups that are attached to the carbon involved in C double bond C, right? Both of them, they are not identical, right? So yes, this double bond, like this group, it will exhibit what? This compound will exhibit geometrical isomerism. So it can be cis or it can be trans. So right now, what do we have in front of us? The isomer that we have in front of us is what? Cis, right? Let's draw one more. That would be what? That would be trans. So in trans, both of the H, they will be on the opposite side of the C double bond C. CH, double bond CH, C2H5, CH3, right? So this is what? This is trans. Right now we are just focusing on the first double bond. Now what about the second double bond? Let's have a look. Okay, so what do we have here? C double bond C, H, CH3, H, C double bond C, H. Here also what do we have? We have C2H5 and H. Correct. So here what I have done is now we are focusing on the second double bond. So what do we see here? The first double bond is cis. Like, what about the second double bond? Or I should say the arrangement around the first double bond is cis arrangement. Now, what about the arrangement in the second double bond? Right now, if you can see, both of the hydrogen atoms, they are on the same side of the double bond. So this is also cis. So can we name this isomer as cis-cis isomer? Correct. And similarly, if H is on the opposite side and C2H5, if we have it here, now both of the hydrogens, they are on the opposite side. So which isomer is this? This is trans, right? However, the arrangement around the first double bond, right, that we have is what? Cis. So this isomer becomes what? This becomes cis-trans isomer. Correct. Now let's have a look at the other isomer in which the first double bond, the arrangement around the first double bond was what? Was trans. So C double bond C, H, CH3, C double bond C, H. Here we'll have H, C2H5, and here also we have H. Right. So the arrangement around the first double bond is what? Trans. Now, if we look at the second double bond, right now what do we have? 2 hydrogen atoms on the same side. So this gives to what? This gives rise to trans cis isomer, right? Now, what would happen if the C2H5 is above, or let's say, on the same side of H, and there is 1 hydrogen atom which is on the opposite side of the H, right? And what is the reference here? The reference is the double bond here. So now we can see that the arrangement around the second double bond is what? Trans. So this is what? This is trans isomer. So how many isomers do we have here if we have 2 double bonds in this compound? Well, there are 1, 2, 3, 4. We have 4 geometrical isomers. Let's have a look at the options given to us. Well, the option A is the correct option. Let's have a look at this question here. So here we have been given an equation, a reaction, right? So SO2 gas plus NO2 gas, they are in equilibrium with SO3 gas and NO gas, right? So Kc, equilibrium constant for this reaction is given as 16, and we have initially taken 1 mole of each of these gases in a 1 liter container, and we have to find the concentration of NO2. We have to find out the concentration of NO2 at equilibrium. Okay, so let's see what reaction do we have here. We have SO2 gas plus NO2 gas in equilibrium with SO3 gas plus NO gas. Right, and the equilibrium constant for this reaction is 16. Okay, initially at T is equal to 0, we have 1 mole of each of these gases in our container, which is what? Which is 1 liter container, right? What would happen at equilibrium, right? But before that, or I would say, can we tell what will happen at equilibrium before knowing at what, in which direction this reaction will be going in? So this reaction is what? Reversible reaction, right? It can proceed in forward reaction, it can proceed in backward reaction as well. How do you get to know in which direction is it going? If you have only the reactants, right? If you do not have the products, then we know for sure that it's going in the forward direction. However, right now we are given one mole each of the products as well. So first thing that we have to find out is in which direction this reaction is proceeding. And how do we do that? We find out the reaction coefficient, right? That is QC. So reaction coefficient is equal to what? The product of the concentration of the product raised to the power their stoichiometric coefficients, which will be concentration of SO3 into concentration of NO divided by the product of the concentration of the reactants raised to the power their stoichiometric coefficients. So that will be concentration of NO2 multiplied by concentration of SO2 gas. Okay, so what is concentration? That is molarity in this case, right? Number of moles divided by volume. And we know that all these 4 gases have 1 mole only in the container. Each of them have 1 mole. And the volume of the container is 1 liter. So the concentration comes out to be what? 1 into 1 into divided by 1 into 1. So that is QC comes out to be 1. Now since QC is less than KC, right? If QC is less than Kc, that means the reaction will proceed in the forward direction, right? Okay, now since we have established that, let's now proceed with the question here. Sorry, I'm writing that equation again. Give me 2 minutes. So this is SO2 gas. This is SO3 gas in the product. Okay. So initially we know that we had 1 mole each of these gases in our 1 liter container. Kc is 16. At equilibrium, what would happen? Now we know that the reaction is proceeding in the forward direction, right? So the SO2 and NO2 will dissociate. So let's say their degree of dissociation is alpha. So 1 minus alpha, 1 minus alpha, right? And SO3 and NO will be produced. How many moles would be there? 1 plus alpha, 1 plus alpha, right? So what would be the value of Kc? So that will be concentration, the product of concentration of the product raised by the stoichiometric coefficients. So SO3 concentration into NO concentration at equilibrium, right? So this is the only difference between QC and Kc is what? That for Kc we take the concentration at equilibrium. QC concentration can be at any stage. Okay, so this will be concentration of SO2 into concentration of NO2. Okay, so what is concentration? Number of moles divided by volume. Volume is 1. So we can equate it in terms of number of moles as well, right? So this comes out to be 1 plus alpha into 1 plus alpha divided by 1 minus alpha into 1 minus alpha. So this comes out to be, Kc is 16. So this is 1 plus alpha square divided by 1 minus alpha square, right? So if we take the square root, what would happen? 16 will become 4, right? So this becomes 4 minus 4 alpha is 1 plus alpha. Okay, so 4 minus 1 is 5 alpha. Alpha comes out to be what? Alpha comes out to be 3 by 5. That is 0.6, right? So 3 by 5 is 0.6. What did we need to calculate? We need to calculate the concentration of NO2 at equilibrium. Okay, so this is what? This is number of moles of SO2 at equilibrium. This is number of moles of NO2 at equilibrium. So if alpha is 0.6, then it becomes what? 1 minus 0.6, that is 0.4, right? So there are 0.4 number of moles. So number of moles of NO2 gas at equilibrium is 0.4. And what do we know? We know that the volume is 1 liter. So concentration will come out to be what? Concentration will be number of moles upon volume. Number of moles is 0.4. Volume is 1. So what do we get? We get 0.4 mole per liter, right? So which option does it match? Well, we know it matches option C, which is the correct option here. Let's have a look at this question. So in this question, we are given 3 hypothetical equations, right? 3 hypothetical reactions. So the first reaction is A is in equilibrium with B. And for that, the equilibrium constant given is 2. The second reaction is in which B is in equilibrium with C. And the equilibrium constant given for that is 4. The third reaction is in which C is in equilibrium with D and the equilibrium constant is given as 3. And we have to find the equilibrium constant for the reaction in which A is in equilibrium with D. Right? So the first thing that you have to do is you have to achieve or you have to arrive at this reaction in which A is in equilibrium with D through these 3 reactions. Right? And how would you do that? Well, let's see. So if A is in equilibrium with B, B is in equilibrium with C, C is in equilibrium with D, right? So what would happen if you add these reactions, right? So the reactant in the reactant B, right, that will get cancelled with the product B. Similarly, that happens with C as well. So what is the equation that you have got after adding these 3 reactions? Well, what you have got is A is in equilibrium with D. And that's what we wanted to arrive at, right? Now, what happens to the equilibrium constants if you add up the reactions? Let's say, so in the question, we have been given that for first reaction, the equilibrium constant is 2. For the second reaction, the equilibrium constant is 4. And for the third reaction, equilibrium constant is 3, right? So what we have done is we have added these 3 reactions and we have arrived at the reaction what we wanted. But what we want is the value of equilibrium constant for this reaction, in which A is in equilibrium with D. So what happens to these equilibrium constants when you add the reactions up? Well, they get multiplied. So the equilibrium constant for this reaction, in which A is in equilibrium with D, it will be equal to what? K1 multiplied by K2 multiplied by K3. Very easy, right? So what would you get? 2 into 4 into 3, that is 24. Let's see which option does it match. Well, it matches our option C, which is the correct option.